Preparing for a software engineer at KPIT interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Tell me about a software project you are most proud of. I'm proud of an embedded diagnostics module I developed for a vehicle controller. I implemented message handling, validated inputs, and added automated unit tests using C and a hardware simulator. The main challenge was preventing timing-related failures when several requests arrived together, so I introduced a deterministic state machine and timeout handling. Code reviews and static analysis caught edge cases early. The project reduced diagnostic response failures significantly and taught me to prioritize reliability, traceability, and clear interfaces. While answering, explain the project's purpose, your exact contribution, technical decisions, challenges, testing approach, measurable results, and one lesson relevant to KPIT's automotive, mobility, or embedded software environment. Question 2. How would you explain the difference between a process and a thread? A process is an independent execution environment with its own address space, while threads share the process's memory and resources. Threads are cheaper to create and communicate through shared data, but that sharing introduces races and synchronization problems. Processes provide stronger isolation but require inter-process communication. In an embedded controller, I would use threads only when concurrency improves responsiveness, protect shared state with appropriate synchronization, and avoid creating more tasks than the real-time system can reliably schedule. Make sure to cover memory isolation, resource ownership, scheduling, communication mechanisms, context switching costs, synchronization risks, and why embedded or automotive applications may prefer carefully controlled concurrency. Question 3. What are pointers in C, and how do you prevent pointer-related bugs? A pointer stores the address of another object, allowing indirect access and efficient manipulation of memory. I prevent bugs by initializing pointers, checking for null where appropriate, respecting buffer boundaries, using const for read-only data, and defining ownership clearly. I avoid returning addresses of local variables and set released pointers to null when useful. Static analysis, compiler warnings, sanitizers, and focused unit tests help detect invalid access before code reaches hardware. In your answer, discuss addresses, dereferencing, pointer arithmetic, null and dangling pointers, ownership, bounds checking, const correctness, initialization, and tools such as static analyzers, sanitizers, and code reviews. Question 4. What is the difference between stack memory and heap memory? Stack memory is automatically managed per thread and typically stores local variables and call frames. Heap memory is dynamically allocated and remains available until explicitly released, making it flexible but vulnerable to leaks and fragmentation. Stack allocation is usually faster and more deterministic. For real-time embedded software, I prefer static or bounded allocation whenever possible. If dynamic memory is necessary, I define ownership, check failures, and control allocation timing rather than allocating unpredictably during critical execution. Be sure to mention allocation lifetime, access speed, fragmentation, thread behavior, deterministic timing, recursion, dynamic data structures, and why embedded production software often limits heap usage. Question 5. How does a hash table work, and how would you handle collisions? A hash table converts a key into an index using a hash function, allowing average constant time lookup, insertion, and deletion. Collisions occur when different keys map to the same bucket. Chaining stores multiple entries per bucket, while open addressing searches for another free slot. I would choose a well-distributed hash function, monitor load factor, and resize when needed. For latency-sensitive software, I would also consider bounded behavior and avoid uncontrolled rehashing during critical operations. While answering, explain hashing, buckets, average and worst-case complexity, collision resolution through chaining or open addressing, load factor, resizing, and how predictable performance matters in production systems. Question 6. How would you find and optimize a slow function in C++? I begin by reproducing the slowdown with a representative workload and profiling the application rather than guessing. I identify whether the bottleneck is algorithmic, memory-related, I/O-bound, or caused by synchronization. Then I improve complexity or data locality, measure the change with repeatable benchmarks, and run regression tests. For example, replacing repeated linear searches with a suitable indexed structure can help substantially. I preserve readability and verify that optimization does not violate timing, memory, or safety requirements. In your answer, describe profiling before optimization, algorithmic complexity, representative workloads, memory behavior, compiler optimization, benchmarking, regression testing, and preserving correctness while improving performance. Question 7. What is a race condition, and how would you prevent it? A race condition occurs when multiple execution contexts access shared data concurrently and the result depends on timing. I prevent it by minimizing shared mutable state, assigning clear ownership, and protecting unavoidable critical sections with mutexes or appropriate atomic operations. In embedded systems, I also consider interrupt interactions and bounded lock duration. I inspect lock ordering to avoid deadlocks, use thread-safe interfaces, and test under stress because ordinary functional tests may never reproduce a timing-dependent failure. Make sure to cover unsynchronized shared access, non-deterministic outcomes, critical sections, mutexes, atomic operations, interrupt contexts, deadlock risks, and designing ownership to reduce shared mutable state. Question 8. What is an RTOS, and when would you use one? An RTOS provides scheduling and synchronization services designed to help tasks meet timing requirements. I would use one when the system must respond predictably to events, such as processing sensor data, controlling actuators, or handling communication deadlines. Tasks can have priorities, while queues, semaphores, and timers coordinate execution. The key is bounded latency, not simply speed. I would still analyze worst-case execution time, avoid priority inversion, and keep high-priority tasks short and deterministic. Discuss deterministic scheduling, tasks, priorities, interrupts, synchronization, deadlines, latency, resource limits, and the difference between meeting timing guarantees and merely achieving high average throughput. Question 9. Explain priority inversion and ways to mitigate it. Priority inversion happens when a high-priority task waits for a resource held by a low-priority task, while a medium-priority task keeps preempting the low-priority task. The high-priority task is effectively delayed by lower-priority work. Priority inheritance temporarily raises the holder's priority, while priority ceiling protocols limit which tasks can acquire resources. I also reduce lock duration, avoid unnecessary sharing, and analyze worst-case blocking so the chosen mechanism satisfies real-time deadlines. Be sure to explain high, medium, and low-priority task interaction, blocked resources, priority inheritance, priority ceiling, bounded critical sections, and how scheduling analysis validates the solution. Question 10. What is CAN, and how does CAN arbitration work? CAN is a robust, multi-master vehicle network where messages are broadcast using identifiers rather than destination addresses. During arbitration, dominant bits override recessive bits, so the message with the highest priority identifier continues without corrupting the frame. Nodes acknowledge valid messages and detect errors through mechanisms such as bit monitoring and CRC. I would choose identifiers carefully, control bus utilization, configure termination correctly, and define recovery behavior for repeated communication failures. In your answer, cover message identifiers, broadcast communication, dominant and recessive bits, non-destructive arbitration, priority, acknowledgement, error handling, bus termination, and automotive reliability considerations. Question 11. What are AUTOSAR's goals, and how do Classic and Adaptive AUTOSAR differ? AUTOSAR standardizes automotive software interfaces and architecture so components can be reused across ECUs and suppliers. Classic AUTOSAR targets resource-constrained, deterministic microcontrollers and commonly uses an application layer, RTE, and basic software over an operating system. Adaptive AUTOSAR supports more powerful processors, dynamic deployment, service-oriented communication, and richer applications. I would select Classic for predictable control functions and Adaptive for connected, high compute, or updatable vehicle services, while respecting safety and security requirements. While answering, explain standardization, portability, layered architecture, RTE, basic software, AQ constraints, dynamic services, POSIX foundations, and which vehicle workloads suit each platform. Question 12. How would you design a fault-tolerant sensor processing module? I would first define sensor validity rules, timing limits, and the safe behavior for each failure mode. The module would validate ranges, timestamps, sequence counters, and plausibility against related signals. On failure, it would raise diagnostics, use a bounded fallback or redundant source, and transition to a defined degraded state. I would add watchdog supervision and fault injection tests, then trace requirements through design and verification. The goal is controlled behavior, not merely detecting errors. Mention input validation, plausibility checks, timeouts, redundancy, safe defaults, watchdogs, diagnostic reporting, degraded operation, fault injection, and traceability from requirements to verification. Question 13. How do you approach unit testing and integration testing for embedded software? Unit tests isolate a function or module using mocks, stubs, and controlled inputs, making failures easy to diagnose. Integration tests verify interactions among drivers, middleware, tasks, and hardware interfaces. I cover normal, boundary, invalid, timeout, and recovery scenarios, then use hardware in the loop for timing and electrical behavior that simulation cannot represent. Coverage helps reveal gaps but is not proof of quality. Every defect should become a regression test, especially in safety-relevant code. Make sure to distinguish test scope, mocks and stubs, hardware in the loop, boundary conditions, coverage, regression automation, timing behavior, interface contracts, and tests for both nominal and fault scenarios. Question 14. What is the software development lifecycle for an automotive embedded project? I view the lifecycle as a controlled flow from stakeholder and system requirements through architecture, implementation, integration, verification, and validation. Each requirement should be clear, testable, version-controlled, and traceable to design elements and evidence. Reviews, static analysis, automated tests, configuration management, and change impact analysis provide continuous quality control. In automotive projects, safety and cybersecurity activities run alongside development rather than being postponed until release. This process makes defects easier to prevent, detect, and audit. In your answer, describe requirements, architecture, implementation, verification, validation, configuration management, reviews, traceability, change control, and compliance with safety-oriented development practices. Question 15. How would you debug a failure that occurs only on target hardware? I first capture exact conditions, software versions, hardware configuration, and failure frequency. Then I add non-intrusive logging, inspect registers and memory, and compare target behavior with simulation or a known good build. I check undefined behavior, alignment, timing, interrupts, stack usage, optimization settings, and peripheral configuration. I form one hypothesis at a time, create a minimal reproduction, and validate each change. Once fixed, I add an automated regression test and document the root cause. Be sure to mention reproducibility, logs, probes, compiler settings, timing, memory layout, race conditions, hardware differences, minimal reproduction, binary comparison, and a disciplined hypothesis-driven workflow. Question 16. What is the difference between a bootloader and application firmware? A bootloader runs before the main application and prepares the device, validates firmware, and can support programming or secure updates. The application implements the product's operational behavior after startup. A robust design separates flash regions, checks image integrity and authenticity, manages version compatibility, and retains a recovery path if power fails during update. I would also prevent unauthorized images, verify transfer completeness, and ensure the device enters a safe state when no valid application exists. Discuss startup responsibilities, image validation, flash layout, hardware initialization, update mechanisms, rollback, authentication, version compatibility, recovery mode, and safe behavior when an update is interrupted. Question 17. How do you write maintainable and safe C++ for production systems? I make ownership explicit, prefer RAII and standard containers where their costs are acceptable, and use const correctness and strong types to prevent misuse. I avoid raw owning pointers, undefined behavior, hidden global state, and unnecessary inheritance. For constrained or safety-critical targets, I follow the project's approved subset, exception policy, and coding standard rather than applying features blindly. Small interfaces, meaningful names, static analysis, peer review, and tests make the resulting code safer to change. While answering, cover RAII, ownership, const correctness, strong types, exception policy, encapsulation, avoiding undefined behavior, static analysis, coding standards, and choosing abstractions appropriate for resource-constrained targets. Question 18. How would you investigate a memory leak or buffer overflow? For a leak, I map every allocation to its owner and release path, then use allocation tracing or a leak detector to identify unbalanced lifetimes. For an overflow, I inspect array bounds, length calculations, copying APIs, and adjacent memory corruption. Sanitizers, static analysis, guard regions, and stack monitoring are valuable during development. I reproduce the issue with a focused workload, fix the ownership or boundary contract, and add a regression test covering the original failure. Mention ownership analysis, allocation and release paths, boundary checks, stack monitoring, sanitizers, static analysis, corrupted metadata, reproducible workloads, and regression tests that confirm the fix. Question 19. Describe a time you disagreed with a teammate about a technical decision. A teammate preferred adding a complex framework, while I favored a smaller module because the target had tight memory limits. Instead of debating opinions, we listed requirements, measured both prototypes, and compared memory, latency, testability, and maintenance risk. The data showed that a lightweight design met the current needs, but we retained an extension point for future growth. We documented the decision and moved forward together. The experience reinforced that evidence and shared goals resolve disagreements better than seniority. In your answer, demonstrate respectful communication, evidence-based comparison, requirements alignment, experiments, risk analysis, compromise, ownership of the decision, and what you learned from the outcome. Question 20. Why do you want to join KPIT, and how would you contribute as a software engineer? I'm interested in KPIT because it works on automotive software, mobility platforms, and the transition towards software-defined vehicles. My strengths in C or C++, debugging, testing, and structured problem-solving would let me contribute to reliable embedded features from requirements through validation. I also value working with cross-functional teams and learning domain standards such as AUTOSAR and functional safety. I would bring disciplined engineering, transparent communication, and a willingness to improve both product quality and development processes. Be sure to connect your skills to KPIT's mobility and automotive focus, mention embedded or software-defined vehicle interest, customer collaboration, quality mindset, learning ability, and a specific contribution you can make. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.